Hello, nice to see such a large turnout here. Please welcome Nikolay Sivko, who will tell us about and enlighten us about zero instrumentation observability based on eBPF.
Cool, let's start. I'm Nikolay. I'm going to talk about observability. I'm few words about me. I'm an ops guy in terms of, in DevOps, ops part closer to me. I worked as a head of infrastructure in a pretty big Russian-based company before. Then I started to build different products in the observability space. Now I'm CEO and co-founder of Corut. Corut is an open source observability platform, and we try to focus on extracting meaning and answers from telemetry data. Check out our GitHub. So let's start from the very beginning. What is observability? From my perspective, observability is being able to answer questions about your system. These days, our systems became super complex. In many cases, we can deal with hundreds or even thousands of services. We need to understand it. We need to be able to quickly identify the root cause of an incident. We need to compare our system behavior before the incident with the current state, and so on. And we need to be able to do so for three reasons. I like to think about it from business perspective. We earn money from our users, and we should provide them with, continuous service. Our app, website, and anything else should be available as much as possible, and we should reduce downtime to provide users with better experience. The second thing is performance. As we all know that there are a lot of researches on that and how application latency can impact our revenue. There are some numbers from big guys such as Amazon. And the last part is cost. We run our infrastructures in clouds, and we should be able to understand how resources are consumed. We should be able to identify the most resource consumers, and it's a part of observability. And why we are talking about observability, eBPF, zero instrumentation, I have few notes about it. I am a relatively old guy, so I started my career at the time when we have pretty straightforward systems. We had some monolith application and databases. Dedicated nodes, maybe a few dozens nodes, and it's pretty straightforward to manage such systems because it's easy to follow the application flow to understand what's happening. For example, in application where we have a monolith application and database, if something goes wrong, we need to check application, or if it's okay, we can check our database, its performance, and so on. And then we can check underlying hardware, underlying storage systems, and it's pretty simple. These days, I don't know why. I don't have an explanation on how we get there. But now we can have even a small project, we can have hundreds, even thousands of services, many databases, and all the stuff runs on pretty dynamic infrastructure. Cloud, we have spot nodes, we have that can appear and disappear many times a day. We have elastic databases, we have serverless, and to be able to manage this, we need to cover this with metrics, schemas, and we should be able to imagine how it works. We should be able to understand the big picture of it. And for example, in this scenario, we should be able to follow the request flow from the ingress controller, if you're talking about Kubernetes, and we should be able to traverse dependency graph and understand how it works and where is the bottleneck. Let's talk about steps that needed to make our system observable. The first step is collecting data. So we are talking about analyzing data. The first step, we need to somehow to collect this data. There are two different ways. We can instrument our applications manually, or we can use some magic, such as eBPF, and automate this process. Then we need somewhere to store this data, some databases, and a lot of talks in this space are about storing telemetry data. We have Prometheus for metrics, we have some replacements such as Victoria metrics and so on. We have many storages for logs such as Elasticsearch, ClickHouse, and many other modern technologies. But I believe that the most tricky part of it is understand this data. How, for example, we have 4 terabytes of logs. So how can we understand where is the problem? We cannot read them line by line. We should be able to extract some patterns. We should be able to query data somehow. And now, like in most cases, it handled manually. And we, with our product, trying to change this. But before we will talk about eBPF, let's talk about what we want to see instead of how to get all this data. I have pretty interesting thought experiment. Like I ask people a lot about, what do you think, how many different failure scenarios can happen in a distributed system? And answer is that it's like infinity. We have many failure scenarios, and we cannot cover them all. And then I ask him, can you please write it down? Like scenario, next. And usually this list ends up with 10 items, only 10 items, because I observed many times how infrastructure engineers troubleshooting issues on production, and all of them act like in a similar way. They have a set of hypotheses about some problem, and they just check them one by one. Like, okay, we have problem with this service. Let's check CPU consumption, possible issues related to CPU, lack of CPU time or something like that. Let's check memory subsystem. Let's check I/O subsystem if we have a stateful application. And then we can check application logs and follow the dependency graph. Like, let's check database it communicates with. Let's check other services. Let's check network between them. And it's pretty limited set of hypotheses. And to be able to detect the root cause, we need to collect the right telemetry data. And how we can collect it We can instrument our applications, for example, to report their latency, their status codes, resource consumption. But in many cases, it will not work efficiently because we have third-party services, and we can deal with legacy services, and we cannot change their code, or it's like legacy programming languages and so on. Ask any guy from the bank industry. And it's tricky to cover with such observability all your infrastructure, because usually we have few pretty critical, business critical services, and many services that it's not critical, but we have to run them, like some periodic jobs or something like that. And usually this part of infrastructure is not instrumented by any SDKs like our OpenTelemetry SDK. And we try to build an observability platform that can gather everything without the need to change application code. And here is eBPF technology. It's like a part of Linux kernel. And it's not so modern, but now we have in production like 90% of infrastructures has kernels already with eBPF support. So we can rely on it and use it freely, and don't care about old legacy version of Linux kernels. So what is eBPF? eBPF is a feature of Linux kernel that allows you to run your own small programs, and these programs can be attached to any kernel function. It can be also attached to a user space function call, and we can process such data in the kernel space and then send it to some user space program for further analysis. And eBPF itself doesn't solve any observability or security problems. It just provides you a way to instrument kernel or your applications. So here are few core key principles or key concepts of eBPF. We have kprobes. Kprobes is a type of eBPF program that can be attached to any kernel space function call. For example, if you have like in the kernel function that called every time that we made a TCP connect, your eBPF program can be will be triggered, and you will have access to these function arguments and returning values. So it's pretty dynamic, and we don't need to have some additional support in the kernel. But everything is trade-off. So in this case, trade-off is that in the kernel we have pretty dynamic functions, so it can be changed anytime because it's not a public function. So it's like internal kernel function that can be renamed, that their arguments can change. And to address this, developers of the kernel decided to put some static trace points into the kernel, and we have some sort of guarantees that the API will be stable. So instead of using kprobes, we can use the static trace points. They already set in some interesting places in the kernel. They can we have trace points for every system call, means when the user space program calls some kernel function such as TCP connect, file opening, and so on. And the third way to use eBPF, we can attach to user space program function call. For example, we have a Python application, and we can attach our eBPF program to a function that's responsible for acquiring global interpreted log. So we can instrument our application without changing any code, and being able to trigger our program on each log acquisition, for example. And to be able to store something while working with eBPF, eBPF has a concept called maps. Maps is some memory storage in the kernel space, and programs can set or retrieve values from such maps. Like it's pretty optimized, and programs can store something between calls. So it allows us to, for example, to trigger the program on TCP connect, and then, for example, set our timer, and then get this timer on when connection is established. So we can calculate, for example, in the kernel space, connection time. And to exchange data between kernel space and user space, there are perf maps. Perf maps are ring buffers that allows you to send data and subscribe to data flow from the user space. And these perf maps guarantee that eBPF programs will not stop when this buffer is full. So in case of where our user space program cannot read the data like as quickly as we need, we just lose some data between kernel and user space, but we have guarantees that our eBPF programs will not impact our system performance. So, and the notice here is that it's good to know how it works, but I believe that not every developer should write eBPF programs, because we have a lot of common pitfalls in our infrastructure, and as we implement something and open source it, you don't have to dig into and develop your own eBPF agents and so on. So I believe especially our product can help you not to write eBPF programs, because it's pretty tricky. So few words about our approach and how we use eBPF. We have a node agent. It's an agent that should be set deployed to all nodes in your cluster, and it gathers information about all applications running on this node. So it gathers a lot of telemetry data. It gathers metrics, logs, traces, profiles, logs, and it analyzes logs right on the node, and it tracks network communications between applications in the cluster, and it uses eBPF. And let's see how we implemented this. So here is the list of trace points or some functions that we cover with our eBPF programs. First of all, running on the node, we need to know about every container, every process running on this node. It's super important to have a full picture, because from other signals, we receive only process IDs, and we need somehow to understand meta information about about every process, its container labels, and so on. So first of all, we need to track new processes on the node. We use trace point task new task, and our program receives signal from the kernel, like new task with process ID 123 is born, then our agent in user space checks the procfs and gathers some metadata from procfs. It determined the relevant C groups, it determines and the relevant container name, and then we also need to check process exit. It can be crash, it can be like normal process exit, and we need this to update our map. We need to know this for some metrics. For example, we track application container restarts, and in some cases, such as when a process has been terminated by the out-of-memory killer, we need to know the reason behind this process termination. We also use trace point mark victim. We remember the PID that will be killed immediately after this program. And then when a process is terminated, we can look up this process ID in the kernel map and like enrich our event with the reason, like this process has been terminated because of out-of-memory killer. And also we use syscalls like file openings. It can be like in Linux, it's two different syscalls to open files. We need this to discover application logs, and also we need to understand the relevant partitions this particular container communicates with. Then we need to track TCP connections because we want to know services that our container communicates with. For example, if we use manual instrumentation, such as we integrate OpenTelemetry SDK into our code, we can know that, for example, we instrumented HTTP calls, for example, but our process also communicates with the Postgres database. And if you didn't instrument SQL library, you will never know that these two are communicating. And using eBPF and especially TCP information, we can cover 100% communications without any gaps, and we will see everything. And we use several places in the kernel to gather such information. The first one, we track syscall connect. Then we track changing connection states, and allows us to understand that this particular connection were established or failed, and we also track connection time. So we know the status of each connection, and we know the connection time, connection latency. And then we track TCP retransmissions that are super helpful when we have to deal with network issues such as packet loss and so on. Like Linux, for example, Linux kernel has only one global counter of TCP retransmissions per network namespace, and our using eBPF here allows us to understand endpoints between where we've seen TCP retransmission. It allows us to track packet loss between any particular services in our infrastructure. Then we want to track application level protocols such as HTTP, PostgreSQL, MySQL, and so on. And we use our agent also to identify application level protocols within TCP connections, and we can identify the protocol in the kernel space and then parse the protocol to understand better statuses and latency in the user space. And we track many syscalls, like write to some file descriptor, which can be socket or file. But it's like in Linux kernel, it's tricky because there are many ways to communicate with a socket. We cannot write with multiple buffers. We can use send message. We can use some send message with some control payload and so on. And this place, it was tricky to implement. There are a variety of ways to communicate with sockets, and I believe we found them all. Here, and to ensure that our eBPF program, like in eBPF, we are super limited in program complexity because the kernel has a validator, and when you load your program, it checks the complexity. For example, you cannot use loops in your eBPF programs. And since we are super limited, we had to split our processing in two phases. The first one is a kernel space. It's super optimized. It uses small fraction of data to detect protocols. And the user space part, which can parse protocols and extract some data from it. For example, let's see how we can track what's happening inside our call to google.com with HTTP. The first one, we have send message from our DNS client with file descriptor number 7, and we can see in payload, we can see DNS request. Then our program calls receive from syscall on this file descriptor and waits for answer from our DNS server. Then we have TCP connect syscall, and we see file descriptors. I repeat file descriptor because it's super important, because we, for example, at this stage of TCP connect, we know the IP address. And then when we communicate with this service through this TCP connection, we don't see any metadata of it, because at the eBPF you only have process ID and file descriptor. After TCP connect, in the best case, we have send to syscall from our program, and we can see HTTP payload. We use this payload to identify protocol within this connection. It should be super simple and super performant. And then finally, we have receive from syscall, and we receive payload with HTTP response. So in this case, we also try to find, we remember at this stage of HTTP request, we remembered that we've seen a request within this connection, and on the stage of HTTP response, we expect that it should be HTTP response, not PostgreSQL data packet. And here is how it looks in the eBPF program. It's pretty stupid, simple program that tries to analyze HTTP request. It tries to match well-known HTTP methods. That's it. So if we see an HTTP method, we most likely it's HTTP request. And why most likely? For example, you instrumented your application and write all the payload to some log, and it can be false positive here, but then we expect that we should have a HTTP response, and here we check the HTTP 1.1 we expect a 3-digit HTTP status here, and in case of our false positive, when we write HTTP payload to logs, we most likely don't write response to this log, and like according to our tests and feedback from our users, this approach works well. So, but these days nobody communicates with services without an encryption, and it's super tricky because at the kernel level, when we track only syscalls, we can only see encrypted data, and we cannot understand we cannot identify the protocol here. But there is a solution, because like these days we have several ways to communicate with TLS libraries. We have many programs that use OpenSSL, and we can track it. In case of Golang programs, they have their own TLS library, and Java has their own TLS implementations, and we can track them with uprobes. In our agent, we implemented only 2 cases, 2 scenarios with OpenSSL and Golang, and it covers like 80% of scenarios according our usage statistics. And we can use uprobes and see the data before the encryption and after decryption. And this means we don't need to implement something special. We just need to set up our uprobes somehow to understand underlying file descriptor, and that's it. And it's like, when we deal with kprobes, when we try to implement a program that triggers on kernel function call, we don't. We just load it into the kernel and like say, I want this program to be triggered when TCP connect happens from any process running on the node, and it works. In case of uprobes, you need to understand that this particular process uses OpenSSL. We use like some Linux black magic to identify it. Then we need to find the offset of probe points within this, for example, OpenSSL shared library. And then we can attach our eBPF programs to the particular PID with particular probe points offsets, and we should track new processes, understand that, like detect OpenSSL usage and so on. It's like much more tricky than using kprobes. And a few words about performance impact. Linux kernel provides you with some validator that check every program loaded into the kernel, and it rejects programs with complexity level more than allowed. And this is implemented because if we run our non-optimal program in the kernel space, we can reduce our system performance. Nobody wants it, and that's why we built rules, a validator, and we can have some guarantees that no eBPF program can significantly affect our system performance. And it's like, from my perspective, it's a pretty good trade-off for observability, because observability, it's critical part of your infrastructure, but when we choose from having high-performance application and pretty accurate observability, I would choose application performance. So in worst case, we just lose some data, and it's not a big deal. Then I want to talk about what we can do with all this data we collected using eBPF. And I will use some our approach at Kahoot, how we use it. First of all, we use TCP connection and application protocols metrics to build a service map. We can understand the big picture, how our applications communicate with each other, the latency between them, any connection failures, any latency issues, and so on. And using eBPF allows us to achieve 100% coverage, because if you run your third-party service on some node, you cannot instrument it manually with OpenTelemetry or something, but eBPF tracks everything, and that allows us to like, for example, to see how a Linux system utils communicates with, Ubuntu website to download some updates, for example. So we see everything, and this is pretty good to know how it works. And sometimes we've heard that our users use such service maps to onboard new developers into their teams, because they can easily, like, say, here we have service, it communicates with that, they use this database and something. We have service map, which aggregates individual containers into applications, but we track any particular TCP connections. That means we can understand low-level communications. For example, if you have 100 instances of some application that communicates with 3 different databases, we can understand that the problem affects only one application instance. This particular application instance has issue to communicating with this database instance. And we know a lot about each TCP connection. We know network latency in terms of like ICMP latency. We know the number of requests between each instance and its dependencies. We know all errors, connection errors, application level errors. We know everything related to packet loss, TCP retransmissions, and so on. And then we can track DNS requests made by each particular service. For example, we know that this pod tried to resolve some, statistic service. We've seen a lot how, you install MongoDB with a Helm chart, and we understand that it communicates with MongoDB analytics server, and we see everything, and it's pretty interesting sometimes. About DNS, like everything is a DNS problem, as we all know, and here we can track not only like DNS queries but their latency, and it's super interesting because in, for example, Kubernetes clusters, it's pretty common issue where like they use DNS for service discovery, and sometimes DNS latency issue can affect your application performance. And we have like predefined checks that allows you to quickly identify any issues related to DNS performance. Also, based on eBPF, we can also generate some tracing data. We not only calculate the number of requests, their statuses and latency, we can see each particular request. It is pretty useful when you drill down into some latency anomaly, for example. You see the particular request, you can see its latency, its status. eBPF tracing, I don't think it's like full feature distributed tracing in this case, because we don't have a tracing ID, because we cannot connect part of like distributed request because we need something, and that's why I like to consider this as like tracing spans instead of traces, because we cannot gather them into a distributed trace. And we offer this eBPF-based tracing as a starting point in your observability journey, because, or if you cannot instrument some services, you will have eBPF-based data, but if you want to true distributed tracing, you have to instrument your applications with OpenTelemetry, and Kahoot support both. Also, our agent can collect continuous, do continuous profiling. Like, imagine that the agent every 100 milliseconds can dump stack trace of every process on your system, and it can resolve these stack traces into like human readable stack traces, and we can have a tool that allows you to explain any CPU spike. For example, we can select an area and see a flame graph explaining like which code consumed more time than other. And also we have a super cool UI feature that allows you to compare some like anomaly with the previous period. And few words how it's implemented, because I'm going to run out of my time. How it works: we have node agents on nodes. We have applications simply instrumented with OpenTelemetry. They send telemetry signals into Kahoot instance within your cluster. It stores logs, traces, and profiles in ClickHouse. It's a super efficient way to store telemetry data because of high level of compression. And it uses Prometheus to store metrics. And everything, UI part is already predefined with service map, dashboards, predefined inspections, and so on. It's like highlight you problems instead of pushing you to understand every chart. And I ask you to try Kahoot if you want to, and I will be happy to receive feedback. And it's open source. It can be deployed into Kubernetes cluster. It supports standalone Docker containers, Containerd, bare metal, and dedicated VMs. It supports RDS, AWS RDS instances. It has advanced database support. And like, if you want to have your single pane of glass in a few minutes, just try it. It licensed under truly open source license, Apache 2.0. If you want some enterprise support, you can ask us about some trial. But if you run small infrastructure, I believe you don't need it. We tried to implement the critical set of features in open source. That's it. If you have any questions, I will be happy. Thank you.
Okay, thank you for the great lecture. Is there someone who wants to ask a question?
Thank you for your presentation. This sounds reasonably costly in terms of CPU usage. In your experience, on some, for example, reasonably busy LAMP server, What is the amount of CPU usage that is spent on such system?
According to our benchmarks, the agent consumes like 10% of a CPU, of a single CPU core, processing like request rate at 10,000 requests per second. So we tried to optimize it. We spend a lot of time optimizing the agent, and I believe it's reasonable amount of resources. We consume a reasonable amount of resources. And yeah, we have, according to our anonymous switcher statistics, our agent is now installed on more than 20,000 servers around the globe. So we had a lot of feedback on the performance. We fixed a lot of bugs already, and like optimization is a continuous process, and we are working on it. Like,
thank you.
You have plans for Java observability. You said you support Golang and OpenSSL. Do you support Java TLS?
yeah, we have we found a way how to implement it for Java. Unfortunately, it is nearly impossible to implement purely using eBPF. It requires some Java agent, additional Java agent, and it like compares data from eBPF about TCP connections and data from Java agent, like a small Java agent. Yeah, we know how to implement that, and we have the related issue in our backlog.
Hi. First, thanks for a great talk. So my question is, from my understanding, this works on a Linux kernel. Is it even possible to do on any like Windows-based containers? And if so, did you delve into that in any form or fashion?
I'm a Linux guy, so I've heard some news from Microsoft implementing eBPF on their kernels, but I know nothing about how its state, and I guess it would require re-implementing everything for Windows, and now we don't have any plans, but I'm not sure, maybe.
Of course, thanks.
Do we have somebody else with the question? I guess no, so thank you very much.
Thank you.